I think it will be. Sounds better.
And when do we start? Will
and you can start. And
I can start.
Click this and.
All right. So yeah, welcome to. I don't know how to pronounce it, but I guess it's something like JavaConf. Yeah, what the CRaC Superfast JVM startup. We just have 35 minutes, so I will rush through the slides. So my name is Gerrit Grunwald. I'm working for Azul. We do JVMs and everything related to Java. I'm also a JUG leader, but that's not all that important stuff. So Java, who's the Java developer in the room? Hopefully all of you. So Java is great. We have a great community, as we can see with this conference, and we have hundreds of Java user groups. Is someone a member of a Java user group? Should be more. Go there, it's great. We have thousands of free open source software projects, but the real star of the whole ecosystem is the Java virtual machine. The question is, how does it work? Who knows how it works? Probably you know how it works. So let me give you a very brief introduction. So we start with our source code, which is a Java file, and then we put it into the Java C compiler. Then this spits out the class file, which is bytecode, and this is cross-platform. And then from there, we have a so-called class loader, which is way more complex than this one here, and it just loads these classes into the JVM memory. That's the basic principle. And from there, it gets into the so-called execution engine. And you see the execution engine is more complex. It's not so simple. And if we take a closer look, it has different parts. It has the interpreter, it has a C1 JIT compiler, formerly known as the client compiler, and the C2 JIT compiler, which is formerly known as the server compiler. And then there is a profiler, and there are multiple garbage collectors that you can choose from. So these two JIT compilers work together since JDK 8, and this is called tiered compilation. So they are both available. Before JDK 7, they haven't been available. So you had to choose either client or server compiler. So we just focus on these three parts because that's the important one to understand the CRaC, which is not the drug, by the way. So, but I hope I can get you hooked on CRaC anyway. So it's we have the bytecode in the class file, and the interpreter takes the code line by line, interprets it down to the instruction set of the CPU, and the JVM is watching that. So watching means profiling. So and what it does, it counts method calls and loopback edges. And when a specific threshold is reached, for example, a method was called 1,000 times, sounds like a lot, but it's not really. Then it takes this method, which is then a hot method, and puts it into the C1 compiler. That's the formerly known client compiler. This compiler is, I wouldn't say simple, but it doesn't do any optimizations to the code. It just compiles it down to binary code as fast as possible. That's the main intention, right? So, and then again, this already compiled code is running, and the JVM is again watching and profiling it. And that means again counting method calls, right? So it calls methods, it counts method calls and loopback edges. And in JDK 17, the threshold is 5,000 times. So was this already lukewarm method called again 5,000 times? The JVM takes this code with the profiling information and puts it into the C2 compiler. The C2 compiler is way more complex than the C1. And this one can optimize the code really highly. It uses so-called speculative optimization. So that means the JVM speculates when it sees the code, and then it sees, oh, there's a branch, and it looks like only this part of the branch is called all the time. I optimize only this branch. And that leads to the fact that it could happen that suddenly the other branch is called, and then the JVM has to de-optimize, but I will come to that. So because we have this execution cycle, and it starts with interpretation, which is slow, then we have profiling, finding hotspots, then we have the C1 compilation phase, fast compile, low optimizations, again profiling, and then C2, right? And then we have really high performant code. And then you see this other bridge, and this is de-optimization. That's what I mean when the code that was what it was optimized for wasn't really called, but the other branch, for example, then the JVM has to de-optimize the complete method and do the whole thing again. Goes back to interpretation, C1, C2, and then with the complete method. That's the idea of de-optimization. If we take a look at the performance graph, then we see three colors here, the yellow, the green, and the blue, where the yellow is the interpreter, and you see it's really just very shortly in the beginning. Then the green phase is compiling and profiling, And then the blue phase is compiling and optimizing. Yes. And then we see this periodic gaps on the right side here. And this is usually garbage collection pauses. Even if you have something like ZGC, which is pauseless, there are pauses. They are just so small that you just can ignore them, but you will see them in graphs like that. Okay, and then we see other gaps. This ones. This is de-optimization. You see that the code was already fast. Suddenly it drops, the performance drops down. It drops really down to interpretation, and then it goes back up again. Right? This is de-optimization. And you see the performance increases over time. So it's not directly fast. So that's all great, right? But it takes time. And if we take that knowledge to microservice environments, then it means we start up the service the first time. JVM has to go through this curve to optimize. Second run, third run, and that sucks, right? This is what people really complain about when they talk Java in the microservice environment is not really nice because it's so slow, right? Wouldn't it be great if we can do something like that? We do it once, and the second time we call the service, we just go like this, full performance from the beginning, right? That would be nice. Second time, third time again. So that would be a nice solution. So let us take a look what solutions are already available. So there is class data sharing. Does someone know what that is? CDS? This is in principle, you have the class loader in the beginning, as we saw, and the class loader collects all these classes and loads them. That means they load it from the class path. Takes some time, means open files, read them, close them. If you can do instead this only once, and then you save these files in a specific representation in one file, it means the second time you start the JVM, it just loads the one file, and that's way more faster than loading all the different files, right? So this is the idea behind CDS, and then you can share these files if they are JVM related. You can share them between different JVM starts. But it also means it's no optimization. There's no compilation or hotspot detection or something. This is plain class loading time. And you might wonder, well, we have SSDs. What could probably be the impact? You could get up to 2 seconds faster startup time just by optimizing CDS. And CDS is available per default since JDK 12. So who's on JDK 8? Someone here in the room? 11? 17? The Fearless, 21? Yes. So if you would like to know more, there's a really good blog post from Ionit Balozin about only CDS and how to tune it, because this is not only JVM related, but also app CDS. So for your application, you can optimize CDS, right? So that can really help. And I guess the slides will be available after the session, so you can also, you don't have to do screenshots here. So, but remember, it happens here. Class loading. This is before it even gets into the execution engine. So totally unrelated. Okay, it's nice, but doesn't help us with this performance curve that we saw. Ahead of time compilation, who knows GraalVM? Who's using GraalVM in production? Huh, okay. So ahead of time compilation is exactly what it says, right? So that means we don't have to interpret bytecode here. So there's no analysis of hotspots or something like that. And there's also no runtime compilation of code. That's ahead of time compilation. It's like you know it from C. You take the code, you compile it down, and then you have a binary in the end, right? That's the idea. And then think about this using Java code. The big advantage, if it's a native executable, the startup time is blazingly fast, right? And GraalVM native image does exactly this. Oh, problem solved, right? Well, not so fast. The problem is AOT is by definition static. So that means the code is compiled before it is run, right? So the compiler has no knowledge of what the code is actually doing. He can only do static analysis on the code. Doesn't mean that is bad, but you can imagine if you do something like the JIT compiler just-in-time compilation at runtime, you can react on the behavior of the application, because you can profile during the run, you can profile the application and optimize for this specific use case, where the ahead of time compilation can just do a one-shot best guess and run it. Right? There's one way you can improve it by using so-called profile-guided optimization. This is also nothing that was invented by GraalVM or Oracle. This is a quite old principle. The idea is you run the application first, you profile it, then you take the profile and apply it when you create the binary image. Right? So then again, it's optimized for one shot. It can't really change at runtime. So if we take a look at the performance graph, and this is now guessing, I mean, there are some benchmarks, but it really depends on the application. But in general, you can say that just plain AOT compiled code can be around 60 to 70% of the performance of the JIT, the just-in-time compilation. If you use PGO, then you can get up to 90%. Sometimes you can even reach the JIT. But that means you have to really run the profile first, right? And then for this one use case, apply it and then create it. Okay. If we compare AOT with the JIT compilation, then we see that there are advantages for the JIT and there are advantages for AOT. Right? The biggest disadvantage that I see with native images is the fact that you leave the Java environment and you go into the native space. You have an executable. If this breaks, you have to debug an executable. This is not Java code anymore, and it behaves differently. So it can happen that you run, for example, all your tests, even in perfect condition, 100% code coverage. You have a test for everything. Everything's green. It can still break in the native image because native code is different than Java code, right? You have to keep that in mind. And this is also the reason why you don't see a huge adoption at the moment, because it's really hard to debug native images, right? And they have a lower memory footprint. That means the delivery footprint is lower because an AOT compiled binary only contains the classes that it needs to run, where the JIT, if you drag in a dependency, you get all the classes, right? So that doesn't mean you load all the classes, but the deployment target is much bigger then, because it contains the whole jar. Okay, let's take a look at a different approach. CRaC. Does someone know CRaC? Who's using Linux here? Windows? Mac? Okay. So CRaC is only available on Linux. And it's a Linux project. It's in the kernel since 2013, so that's 10 years already, so that's quite mature. It was made for freezing a running application or container and then save the state of this container to disk, and then at a later point restore back from disk into memory. That means checkpoint restore. Does everybody know what that is? Checkpoint restore? Who has a laptop here in the room? Don't be shy. Probably most of you. If I close this laptop here, just close it, right? And then tomorrow I open it again. It will be exactly here. Because when I close it, the operating system creates a checkpoint. It recognizes, oh, the lid is closed. Save everything that I have, the operating system with all the applications, to the disk. The next time I open it, it finds the checkpoint and restores back to memory. That's checkpoint restore, right? That's the main idea. So that means most of you know that behavior. But this is the idea behind it is to use that for applications in this case. Okay. It's already used by OpenVZ, Linux containers, Docker, and Podman. They don't use it every time, but you can use it, right? So it's not that it's used every time, but you can use CRaC in combination with them. And it heavily relies on the proc file system. The proc file system is a file system that's a little bit strange for people that don't use Linux, because on Linux a file system means that there's a folder. In that folder are lots of files. And these files contain information about all the processes running on the operating system. That means if you can read this folder with all the files and interpret it, then you know a lot about the processes running in the system. Right? That's the idea. And it can checkpoint all these things: processes and threads, application memory, open files and pipes, and all kinds of stuff. Means checkpointing and restoring it back from the disk to memory. And it can even rebuild a TCP connection from one side only, which is quite impressive. Okay. It doesn't come without challenges, of course. Wouldn't be too easy, right? So the problem is, for example, you can't create a checkpoint on this Mac, which is an ARM machine, and then restore it on an Intel Mac. Because this is code for ARM, the binaries. If I take the files, I can put them on the Intel Mac in macOS, but I can't restore because the compiled code that is in the checkpoint is made for ARM and not for Intel, so that won't work. Means you have to have the same CPU architecture. And even there can be differences. So that means if you have an Intel Core i3, for example, and you have an Intel Skylake Xeon processor, the Xeon can do a lot more optimizations than the i3 can. The problem is if you create a checkpoint on a Xeon and then try to restore it on an Intel Core i3, it will break. Because the Core i3 doesn't know all these optimizations. The way around will work. Because the Xeon knows all the stuff from the Core i3. Right? So the CPU level has to be the same. That's one of the problems. Also, if I have an open file here, doesn't mean the open file is on the other system. I can have the checkpoint, but that doesn't mean I have the file on the other machine. I can restore it. It tries to open the file, doesn't find it, breaks. Right? Then, because this is all bound to the PID is on Linux, it's a process ID. So every application you start on a Linux system has an ID. And this is unique in the system. And everything is bound to this ID in the checkpoint. That means if I restore it, it could theoretically happen that this ID is already taken. And then it could break. Right? And another thing is, you would think the Java virtual machine is in principle an application. So I can just checkpoint it, save it to disk, and restore, right? Should work. That's in principle true, and with the plain JVM it will work, but the JVM is just a runtime environment. The problem is not the JVM, the problem is your code. Because your code has the database connection, it has the file open and all these things, right? It's not the JVM itself. If we shut down the JVM and save the state to disk, it will, for example, shut down the database connection. When you try to restore it, the JVM will start up, your application will try to connect to the database, but it's not there because the connection is not there. That's the problem. That leads me to CRaC. That means coordinated restore at checkpoint. And the difference here is coordinated. We try to solve the problem to let the application know when there is a checkpoint and also when it was restored. So we give you some kind of a trigger, right? So that your application is aware of, oh, I will be checkpointed, oh, I was restored, right? That's the idea. It comes with a very simple API. It can create checkpoints either from code or using jcommand. Jcommand is a tool that comes with every JVM in OpenJDK. And it throws checkpoint exceptions. So it can tell you if you forgot to close or open a resource. And what we do is we use so-called JVM save points. Right? If you do a garbage collection, you never do that manually. So the JVM is just doing that in the background. And when it does it, it stops all the threads. Right? Doesn't matter how complicated your system is, how many threads you're running, the JVM stops them, clean up the heap, restarts all the threads. That's a JVM save point. And we use exactly the same. So we can make sure that everything is correctly stopped, and then we can clean the heap like a garbage collection, then we save the heap. In principle, this is more or less a heap dump. We added 2 new commands, which is -XX CRaC checkpoint 2. What we do is we just tell the JVM where should it store the files for the checkpoint. Right, the JVM is running with your application, we trigger a checkpoint, now the JVM needs to know, okay, where should I store the files? This is the path here. And restoring is the same. You just call Java -XX CRaC restore from, and then we equal, and then put the path in there. If there's a checkpoint in that folder, the JVM will just restore everything back to memory. What it does, it really does, the JVM is running with your application, and whenever you decide, you stop it by creating a checkpoint, it will close everything, save it, and when you restore it will exactly start from the same point where you stopped it. It will just continue running, right? Okay, it's an OpenJDK project, so it's led by Azul, by one of our engineers, but it means it's part of the OpenJDK, but it's not part of the distributions at the moment. The reason for that is, if you're a Java developer, you probably know that we have now the module system in JDK, since JDK 9, the JPMS. The Java module system was formerly known as Project Jigsaw. Project Jigsaw was, I don't know how many years it was an OpenJDK project, but it never really became part of the distribution. And this is exactly in the state that we are right now. So we have a project which is an OpenJDK project, and you can get builds from OpenJDK with CRaC, but it is not part of the official distribution yet. We are working on that. So the API, pretty simple. It's just one interface. It's called resource. It has two methods, before checkpoint and after restore, pretty simple. The idea is you implement the interface, and you only have to implement it in the classes where you have socket connections, whatever it is. When you have a database manager or whatever that connects to over a socket to some other place, this is typically the class where you implement this interface. Then the application will be called in case there's a checkpoint. And to make that happen, we have to register this resource in a so-called context. I will come to that. So the idea is just implementing the interface is not enough. The JVM needs to know, okay, you have implemented an interface, that's nice, but should I really call this class? And to make that work, you have to call core get global context on the JVM. There's only one context, and then you register this resource in the context. And then the JVM knows all the resources that are in the context I will call when I have a checkpoint, and also after a restore, I will call these resources. So the idea is you implement the interface, right? Then you get the global context, and then you register the resource in the context. And usually you do that in the constructor and your factory method, wherever you create the class. There you register this resource. Creating a checkpoint, there are two different ways. One thing is JCommand. Like I said, JCommand, you don't have to download, it's part of the JDK. You just call it either with your jar, with the jar name, or you call it with a PID under Linux, and then just call jdk.checkpoint. That's the command. If you trigger the JVM with this command, it will create the checkpoint using CReO in the background. That's the idea that we use here. You can also do it from code. You might ask yourself, why should I do that from code? Because when I create a checkpoint, the JVM will be shut down. Well, we have customers that, because when I saw that the first time, I was like, yeah, okay, it doesn't make sense. But we have customers like high-speed trading companies. So what they do is they run their application, and because they run it in a market where they have to do transactions very fast, and the market opens at 8 a.m. in the morning, right? So that means at 8 a.m. in the morning, they have to make sure the system is completely warmed up and fast. So what they did in the past, they started their servers at 4 a.m. in the morning and applied specific code just to warm up the JVM to get to this high performance curve that we saw, right? So they have specific code to warm up their application. If you have such code, you can trigger the checkpoint from code, because then you know exactly, now I run through all this application stuff that warms up the JVM, now I can just create the checkpoint, right? That's the idea. But it's you don't really need that in general. So typical usage, you run your app in a Docker container, you can create a checkpoint. You now can either save the checkpoint in the Docker container, or you save the checkpoint in a Docker volume, for example. You can even save it wherever outside of the container. If you save it in the container, then you have to commit a new state. This is usually not what you would like to do, but you can do it, and this is the fastest way to create checkpoints. If you do it on a Docker volume, that could be somewhere in your cluster, it's a little bit slower, but SSDs are not really the problem these days. And then you start the container by just pointing it to the external volume or to wherever you have stored the checkpoint. That's the idea. So I already told you it's only available for Linux, for ARM and Intel CPUs. So what about Windows and Mac? If you code on Windows and Mac, then it means there's no JVM that supports CRaC. So it will break because you don't even have the interface available. So what we did is we created a project called org.crac, which is also open source, like the whole CRaC thing. And this is designed to make it easier to adopt the CRaC API. And the idea is just, it's a mirror of the API, So you add that as a dependency to your project, and then you can work with the same resource interfaces in your code. And the advantage here is that the library will figure out on its own if it runs on a JVM that supports CRaC. And if it runs on a CRaC-supported JVM, it will use CRaC. And if not, it won't do anything. So that means it detects CRaC at runtime. And if there's no support, it won't call the interface. And if there is support, it will just call the jdk.CRaC implementation. So that means you can code on Mac, on Windows, and Linux, and as soon as you run it on a JVM on Linux that supports CRaC, it will work. You can get it either via Maven or Gradle, so it's on Maven Central. And it's also on github.com/crack/org.crack. There you can find the implementation and all the code, so it's not really a secret. The big question is framework support, because when you run Java, usually you run it on either Spring Boot, Micronaut, Quarkus, or something like that. And that means these frameworks need to support CRaC to make your application work, because the frameworks itself, they also have resources open, right? And you can't close them, because this is somewhere hidden in the framework. So the support at the moment is Quarkus has, it's rudimentary support. They only support the interface, and that's it. Micronaut has quite good support for it, and Spring Boot 3.2, it's wrong, and Spring 6.1, they have full support. So that means if you have a Spring Boot application and it runs on 3.2, then you can just, and you use, for example, the Spring resources for a database connection, you don't have to do anything. You can just create a checkpoint. The framework will do all the rest for you. You don't have to implement interfaces, right? So that's quite good. Okay, now I talked about all the stuff that it can do, and now let me show you some things. So if we have a Spring Boot application that usually starts up in 3.8 seconds, Micronaut 1 second, Quarkus a little bit faster, but around 1 second. And this is just whatever service we created as a demo because it was slow, right? So it took 4.3 seconds to start. Start means time to first operation here, okay? This is running on a normal OpenJDK build. So if we run it with CRaC after creating a checkpoint, this has been the startup time. And that's pretty impressive, right? So that means the Spring Boot application came up in 38 milliseconds. And this is exactly as fast as native images can be. So that means once you have the checkpoint, it really relies only on loading stuff back from the SSD into your memory. Right? And that's pretty fast. That's also the reason why you see that more or less the CRaC startup times are more or less the same. It's in the same range. Because once it's just a file I/O, it doesn't matter how long it took to start up the whole application. Spring Boot takes some time to start. Right? If you create a checkpoint, then all this stuff was done. You don't have to do it again. It's really just continue running. That's what it is. Okay. As a summary, CRaC is a way to pause and restore JVM-based application. It doesn't require closed world like the native image does. So that means if you use reflection in your application, then what it means is that at runtime, the application will look up other classes. You can't do that with ahead of time compilation easily. Because if you compile ahead of time, then, and you do something at runtime, how should the compiler know that you do that later on? There are ways to do it, but this is the tricky part when working with native images. And you don't have to do it here because this is just a normal JVM. We just stop it and restart it again. So it's extremely fast at full performance level. There's no need for hotspot identification or method compiles or stuff because this was done before you do the checkpoint. So you decide, you start the application, you run it either for a minute or for a day, and you touch as much code as possible in that time, and then you at one point you decide now it's time for a checkpoint, and then you create the checkpoint. And then the next time you start it, it's exactly that fast. There's no difference. We have improved throughput from start. It's an OpenJDK project, and it also can you save some money. So if you run stuff in the cloud, you probably know this curve. On the y-axis, we see CPU utilization, and on the x-axis, we see the time. And what we usually see with the JVM is that you start up the application, and it has this peak in the beginning. That leads to really strange effects, especially in Kubernetes clusters and all that. And then suddenly it drops again. So this is exactly the JVM startup time. That's the curve that we saw. That means there's code that needs to be interpreted and compiled and optimized at the same time where the application is already running. And at some point, everything of these optimizations are done. And then if we create a checkpoint here, right, and restore from there the next time, you don't need that many CPUs anymore. Because then we only need, maybe in this case, 50% of the CPUs, because this peak is gone. That was before we created the checkpoint, right? So and with this, it can save really money. And it eliminates startup time and CPU overhead. If you would like to know more, everything is here, github.com/CRaC. There you can follow the project if you like. If you play around with that, you can even create issues. We will try to fix them as soon as possible. And with this, I'm done. If you would like to get a JDK with CRaC support, you can get it from Azul. If you go to the download page, there you will find something like JDK plus CRaC. And it's for free. You can also use it in production for free. I think this is the link to vote this session. I think I added it there. So if you would like to vote for this session, then you can scan this and do the voting. And I think I'm done. I'm not sure. I think I'm on time. I am? Good. Usually the session is 1.5 hours, so it's way more slides, so it's really just a fraction of it. But I hope if you have any questions, then yeah.
Yes, so let's imagine we have a Spring Boot application, and it starts after 5 seconds, but within this 5-second time, it opens connection to databases, to some message brokers. Then you do this checkpoint, right? So when you restore it from this checkpoint later, will it reopen these connections again?
Yes. So the question was, you have a Spring Boot application, you start it up, takes around 5 seconds. During the startup, you connect to databases and kinds of stuff. If you create the checkpoint, will it, after the restore, automatically connect to the databases again? Yes. As long as you use the Spring resources to get the database connection, yes, it does. Otherwise, you have to implement the interface, and then in the before checkpoint, you have to close the database connection, and in the restore, after restore, you have to reopen it. But there's one interesting thing with the Spring Boot stuff. The majority of the startup time is not your application. It is the framework itself. So because they support it completely now, since the latest version, they implemented a feature where you can let the Spring Boot framework automatically create a checkpoint before it starts your application, right? So it will just load the framework, create the checkpoint, and then start your application. This alone saves 80% of the startup time. So I have a demo on GitHub, and I can show you if you like. It's just the Spring Boot pet clinic. It starts up usually with 4 seconds. If you use this automatic checkpoint, that means before it starts the Spring Boot pet clinic, it starts up in 300 milliseconds. And then you don't have to do anything because your application wasn't even started then. Right? So the framework takes a lot of time, especially in Spring Boot. So you can get that down without doing anything in your code if you just use this automatic checkpoint that they implemented. Yes?
Yeah, so this process can be automated to run the Spring Boot.
It will do it automatically. So if you start Spring Boot with this flag, it will create the checkpoint automatically, and the next time you can just restore from that checkpoint.
So you can put it into the pipeline?
Yes, you can just put it in the pipeline. That's the idea. And this is the easiest way. If you have Spring Boot, I would recommend going this way first, because it gets you already down 1 order of magnitude. So you get down from seconds to milliseconds. And then the question is if you need 50 milliseconds or if 300 milliseconds are okay. Because if you do a manual checkpoint, you can get even faster, because then you can also checkpoint your application, right? Because the automatic one from Spring Boot is before the application starts. But this is already, like I said, this is already down to 300 milliseconds with the Spring Boot pet clinic from 4 seconds. So you can even read about it. So they have a lot of documentation on the Spring side about CRaC support, because they added it recently. I think it's a month ago. So it's quite interesting. Any other question? Yes?
Yeah. Since we have to use this JDK with CRaC support, and if you are using some resources this and reopen. Other tools for simplify and focus. We make it on a completely different level, like for example, freeze Docker container.
You can freeze the Docker container using CRaC. It might lead to problems. You have to try it because there's no general rule. So Docker supports CRaC, not CRaC, CRaC, and then you can checkpoint the whole container and restore the container. But you have to play around with it because I never tried that really. It has limitations. And I think we should stop now. And if you have further questions, just come down and then we can talk even outside.